Okay, 3.5, modeling with nonlinear regression. So, a couple things here. We're just going to use like some different functions and model data, I should say. Here, model data, using exponential, logarithmic, logistic functions. So, just going to talk about that and see what we're going to do here. The biggest thing is, what is nonlinear regression? This is the process of fitting an equation to nonlinear data. So you're going to kind of take this data that might not be linear and try to fit an equation to it. Okay, just kind of types of different functions, types of different regression that you see, here. So just kind of taking a look. Linear regression, as you can see right here, the points you try to stretch it into and make it a linear line, right? Basically, right? Quadratics, if you have a certain data point, you can take a look at what the graph looks like. You're trying to stretch it into that type of equation. Power regressions, we know over here that the graph will kind of look like that. So you're basically taking a cluster of points. And the reason we talk about this is in real life, the points don't always add up. You have data and it might not be exactly a straight line, right? Well, I think we talked a little bit about linear regression back in algebra, where you have an actual sample size and you actually have data, but it's not always going to fit a perfect line. So what you try to do in this is you try to fit an equation to it. So using the data you have and say, well, that's close to a line or it's close to a quadratic. And so what can you do? Okay, so an exponential regression, you can see like these points here, they look like they're going upward on an exponential rate. So maybe there's a line that fits them pretty well. Logarithmic function here kind of does the opposite, or similar to that. It goes up, which is not as an extreme. And then you have like a logistic one here where it has this little curve to it. Okay, so just kind of looking at like when we talk about growth or decay, a lot of times we suggest an exponential model in there because we think it's going to grow very rapidly or decline very rapidly. But sometimes when it goes rapidly right away and then it goes slowly over time, that might suggest a logarithmic model. And we calculate those. We actually use those by using the natural logarithmic regression. So that, remember, natural regression means that we're talking about our buddy E when we talk about natural logs. Okay, that would be the base of E. Now, just thinking about that, right? Because if you take a look at these, like this graph here is exponential, it goes up really fast. This one goes up at a rapid rate, but then starts to level off, right? And same thing here, it kind of goes up and then starts to level off. That's what they talk about logistics down here, is that a logistic growth function, a lot of times it goes rapidly right away initially, but then it'll start to level out. And that might be due towards some kind of horizontal asymptote, and it might be due to some limiting factors that we have, just space, food, water, real life things that might happen to something that makes it level off. So you can see kind of here, it starts to go up rapidly like an exponential or like a logarithmic, but then starts to level off at some point, okay? So the big thing really is it's up to you to determine what the graph looks like and what's the best fit model for that data by looking at the graph. And you look at the graph here and then you kind of look and examine the correlation coefficient. What that is, R of the regression. When we think about R, we think basically that's the value saying that this is, when we get that linear regression, our R value, depending on how, usually it's between -1 and 1, and the closest you are to 1, the better. That means that your data fits pretty good based on your R value, okay? If it's 0, if your R value was 0, it would mean that there is no correlation to the data at all, okay? So the closer to 1, the better. A lot of times it's like 0.97, 0.98, and that's R. Again, you might need to test a few models and see and jot down the R value and see what the best value is, how close it is, and we can kind of look from there. Okay, a lot of things to go through here though, so let's make sure we just kind of look through it. One thing we want to talk about is if you didn't get, I'll give you a handout with some of this regression sheet on here, and this part is on there, but if you did not get an R or an R value, R and R squared, when you start to calculate these things, then you need to turn on your diagnostics, and you can do that with the following stuff. Go to second 0 to get to catalog, scroll down and get to diagnostics and hit enter a couple times, and you end up getting diagnostics on and a done message. That tells you that you're ready to go. Now, once you recalculate your regressions, you'll see you get an R and an R squared. And if you can do that, then you know that your regression, you can test your R value and see, well, is it close to 1 or not? Is it a good model or not? If you really want to know more about what R and R squared are, then you can take stats, because stats does a lot more with your R values than we do in pre-calc. Okay, so let's move on. So this first one is an example, and I kind of just want to go through this a little bit with us in class, really, because there's a lot of words here and a lot of numbers and a lot of calculator pushing and just kind of getting things done. But we'll just kind of walk through the program, the problem, and then show what we're doing, and then we'll kind of talk about the buttons you push. But we'll kind of walk through this together in class just to just so I'm not pushing buttons by myself here and you guys aren't seeing it. I think it's one thing we want to do together. So you have this data about Mesa, Arizona, and how fast it grows from the year, and then the population is in thousands, as you can see that kind of written right here, okay? But so when we do this, you kind of can make a scatter plot of it and see what the data looks like, and you know, then we can kind of get an idea of what you know, kind of model we should use. So when we do this one, it's down here in this little window. You can see that the scatter plot of the initial data, and we put the scale and everything down here, what you should use. But if you look at the initial data here, this kind of suggests that it would be, you know, an exponential growth model. And you can take a look at it, and you can see this kind of takes the graph, goes up like that. It looks like an exponential function. So that's one thing we can look at after we make that and say, well, okay, maybe it looks like an exponential function. So that's where we get to step 2 and say, well, maybe we want to find an exponential function to model this data. So I can do that with all of this stuff. It gives us the growth rate of 6.7%. It gives us all sorts of stuff. It gives us, when we put that stuff in, we end up with all these models. We can see that they give us some stats right here, right? So this thing right here is going to tell us all the stuff we need to know when we use the diagnostic feature of the calculator. And so that window right there, like I said, we're going to do it together, kind of gives us a lot of stuff. B gives you your growth rate. You know, A models something else. You know, R is, we talked about your R value, right? These are very, very close to 1. So we know it's a pretty good correlation. And you can see when you actually do the regression by punching all the buttons in here, which we do in class. We will do this in class. Okay, when we do that, you can kind of notice that it matches up pretty good, right? The reason it matches up pretty good is because your R and your R squared value are really, really close to 1. So it's a pretty good indicator. Okay. Down here again are just kind of tips to input the data into the calculator and how to do this. And like I said, we can do this in class, and we will kind of walk through this problem just to show you how we got certain stuff and how to use the calculators in this way, and then how to use the scatter plot stuff as well. Okay, but for the purpose of today, let's just kind of go through some other things as well. All this stuff we can cover in the next class. All right, so the next thing we want to talk about is linearizing data. So when we linearize data, really what we're doing is we're taking the correlation coefficient is a measure calculated from a linear regression. So when we linearize it, maybe it's not linear data, but we want to force it to kind of make a line if we can. So really what we want to do here is we want to linearize something so it can be linearized is the term in order to measure a correlation coefficient or your R value for nonlinear data. So you might have data that's not quite linear but you can try to linearize it to make it a little bit more linear. So we can do this a couple different ways by graphing some points where we change a certain value here, and we kind of change up the equation a little bit. So now we can use the regression model we're choosing to use. That can be really anything, right? It can be just based on what our graph might look like. We might be using a exponential model, or we might be using a power function model, or a logarithmic model, just based on what it looks like initially. So we go back, like on this problem, we could see right away, right here, it kind of looked like, yeah, this looks like an exponential model. So maybe I want to use an exponential model on that, okay? And if the data appears to cluster about a line, then we can say that this model is likely to be a good fit, okay? So that means your R value, good fit, means you probably have a strong R value if it can cluster along in a line, okay? So just an example here shows you that if you've got like some original data, right? If we linearize this, and this kind of looks like an exponential, right? It kind of just goes up on that route here. So if we did that, and we'll show you down below in the table, but exponential data, we kind of keep the x's the same, but we change y to the natural log of y. And now you can see the graph kind of clusters up in a little bit more of a point, okay? Or sorry, more in a line. And so now we might be able to have a good correlation value, good R value, because it clusters to that line. Now, transformations, depending on what we're trying to do. We talked about this one being exponential because we could tell from the original data, it looks kind of exponential. So we did this. We took the x and then the natural log of y. So depending on what your original data looks like, here's all the different ways in which we can transform it. Okay, so just write these down so you can make the correct choice. If it's a quadratic, we know that quadratics are ax squared plus bx plus c. But when we graph those, we're going to actually graph x and the square root of y to linearize these data. Okay, if it's an exponential function, we know exponentials are y equals ab to the x power. So like this is the one we just did the example of. So in that case, we graph x and then take the natural log of y. For a logarithmic function, okay, we know it's a little bit different. We write it differently, right? Logarithmic and exponentials are inverses. So we kind of have that going on. A natural log of x plus b. So if it's a logarithmic function that we see, the graph that we're going to use is natural log of x comma y. Those are the plots we're going to point. And a power function, ax to the b, in this case, we would graph natural log of x and natural log of y. So these are kind of how you change from how you go from your original model to your linearized, or from your original table of values to here. X, y becomes one of these things down here when we graph it. Okay? So let's just do a quick example where I can show you it. And then, like I said, we'll do a lot of it in class with the calculators, but I'll just kind of show you what we're looking at here. Okay, so this first table gives us some values and of consumer price index from 1955, I should say, 1955 to 1997. Okay, so here's the original data. If I graph that, and I'll just kind of sketch what I got when I graphed it, but when I graphed it, I ended up getting something that looked like, okay, these points here, right? It's just do the scatter plot. Again, I'll show you how to do that. And then they kind of started to go upwards like this, okay? So that to me makes me think, all right, this could be a exponential, right? Because it kind of follows that curve. So maybe it's an exponential model. So because it's exponential, I'm going to kind of go x and then the natural log of y. So my x's are all going to stay the same in here, going up by 10 years each time, except the last one. So into 1997. And so now I just take my value here and I take the natural log of that. And I end up getting like 3.29 here, 31.6. Oops. And keep in mind, I'm rounding these values, you know, oh, sorry, this is 30. What am I doing? I knew I did something wrong. So I hit 3.29 is correct. This would be 3.45. This one is 3.99, 4.68 here, 5.03, and 5.08. So all I did was just take these values and take the natural log of them. And now I have my new value, my new data. Okay. So when I do that though, my new value just kind of maybe looks a little bit more linear. Closer, right? I mean, if you think about it, it would be a little bit closer to a line, right? It might not be perfect, but it looks closer. So this was my original graph, my original data. And this was my linearized. Okay, so now what we want to do is we want to find a regression equation for the linearized data. So this is where, when we do this part, what we want to do is we want to kind of do the work that we were doing on this page right here. Kind of step 2, use some of these functions in the calculator to get a linear equation. So we're kind of taking this data now and plugging it in. And now we'll kind of get a linear equation based on our new data right here. Okay, right here. All right, so with that, just saving you the work, because like I said, we'll do some of that in class in the calculator. But what you end up getting is y equals 0.046 x minus 87.976. Well, remember, it's a linearized data, so this is a linear equation. This is y equals mx plus b here, basically. All right, so that would be that. Now, use that equation to find an exponential model. So what we've done, basically, is we've got this new data that's in a linear form, but we're talking about natural log of y. So when it's exponential, I'm going to sub in for y, I'm going to sub in natural log of y and then kind of solve for y that way. So in doing so, and I'll try to be fast here so we can be done because we can talk about it more tomorrow. Basically, my new equation, instead of y, I get natural log of y equals 0.046x minus 87.976. And then I'm going to exponentiate each side. So what does that mean? Remember, we have base e, so I'm going to rewrite it as an exponential form. I'm going to exponentiate each side. So now it's going to become e to the natural log of y goes to e to all of this stuff, e to the 0.046x power minus 87.976, all that exponent. So I just exponentiated, I just took the base. Remember, a natural log has base of e. We just took them to the base e and raised those to the powers. Now, we know that e to the natural log of y ends up being just y here. That's how we solve for y, because we have right here is the inverse property. We know that these are inverses. So we just e to the log of y, natural log of y is y. So y is going to equal this here, e to the 0.046x minus 87.976 power. Okay, that is probably going to be good enough because when you do that, you end up with, you can take it one step further. I can do the product property and make this, I can keep going with this if I wanted to and say, I'll just do it in red here and say y equals, make it product property, say e to the 0.046x minus, or sorry, times e to the negative 87.976 power. They're basically the same thing, and which would, but then when you calculate this out, you get, it doesn't do it in the calculator because it just goes on too far. So that's why this model is actually okay. All right, and finally, the last thing then is what do we do next? Well, we're trying to then predict that model in 2020. So all I would have to do is plug 2020, gosh darn it, plug 2020 into X right here. Again, I could do it here if it's nice and works out, but plug 2020 in there, and I end up getting my prediction for the year 2020. Okay, so we'll stop there because I know there's more, like just going through that's tough, but when we talk through it on the calculator, it might be easier. We'll work through some of those examples next time in class. Okay, we'll see you then.